All right, today we're putting on our detective hats and cracking a scientific code. We've got a mystery on our hands, and the key to solving it, well, it's one of the most fundamental properties in all of science. Let's get right into it. So, here's our case. 4 mystery cylinders. One looks like copper, another one is kind of brassy, one's clear, and the last one's a dull silver. But, looks can be deceiving, right? We need solid proof to figure out what these things are really made of. So that's the big question, isn't it? How do we positively identify these materials? We can't just guess. We need a reliable method, something like a scientific fingerprint that's totally unique to each substance. And that fingerprint, the key clue that's going to unlock this whole mystery, is density. It's what's called an intrinsic property of matter, which just means it doesn't matter if you have a tiny piece or a giant chunk of something, its density is always the same. So, what is density really? Well, to put it simply, it's how much stuff, what scientists call mass, is packed into a certain amount of space or volume. Think of it like this: a suitcase packed with feathers versus one packed with rocks. Same space, totally different amount of stuff inside. And this is the magic formula right here. Density equals mass divided by volume. It's that simple. This little equation is going to be our #1 tool. If we can just find the mass and the volume of our cylinders, we can calculate their density and crack this case wide open. You've seen this a million times. Why does a log float while an anchor sinks? It's all about density. The wood is less dense than the water, so it floats. The iron is way denser, so it sinks right to the bottom. It's the same principle we're using today. Okay, time to start the investigation. To use our formula, we need 2 key pieces of evidence for each cylinder: its mass and its volume. Let's get to it. First up, let's get the mass. For this, we're going to use a quadruple beam balance. This thing is incredibly precise, letting us measure each cylinder down to 1,000th of a gram. And getting this measurement right is absolutely crucial for an accurate result. Okay, mass is recorded. Now for what can sometimes be the trickier part, finding the volume. But don't worry, there are a couple of really clever ways to do this, and we're going to check out both of them. Our first method is the most direct approach, good old-fashioned measurement. This works perfectly for objects that have a regular shape, like our cylinders. It's all about being careful with our measurements and using a little bit of math. So here's the game plan. First, you just take a ruler and measure the cylinder's length. Then, you measure its diameter. Now just divide that diameter by 2 to get the radius. Finally, you plug those numbers into the formula for a cylinder's volume. Pi times the radius squared times the length. And that's it, you've got your volume. But what if your object is all weirdly shaped, like a rock or something? You can't really use a ruler for that. Well, that's where our second method comes in, and it's a really elegant solution called the displacement method. It works like this. You pour some water into a graduated cylinder and write down that starting volume. Then, you gently slide your object in, no splashing. The water level goes up, right? You record that new, higher volume. The volume of your object is just the final volume minus the starting volume. Simple. Oh, and before we move on, just a quick but super important reminder. Safety first. Anytime you're in a lab, especially with glassware around, it's goggles on. Always. All right, detectives, this is it, the moment of truth. We've gathered all our evidence. We have the mass, and we have the volume for every single one of our cylinders. It is time for the final calculation. So we bring it all back to our trusty formula, density equals mass divided by volume. We're just going to take the mass we got from the balance and divide it by the volume we just figured out. The number we get is the final clue. So we've done the measurements, we've done the math, and now it's time for the grand reveal. Let's compare the densities we calculated to the known densities of different materials and see if we've got a match. And would you look at that? Perfect matches all the way down. Our first cylinder clocked in at 8.96 grams per cubic centimeter. That's a spot-on match for copper. Number 2, 8.40. That's brass. The third one, 1.18, is a dead ringer for acrylic. And our last one, 2.70, is definitely aluminum. Case closed. Okay, so we figured out what a few cylinders are made of. That's pretty cool, but what's the bigger picture? I mean, why does knowing how to do this actually matter out there in the real world? Well, it turns out this one skill is huge in so many fields. Geologists use it to identify rocks and minerals. Forensic scientists might use it to connect evidence to a crime scene. Engineers absolutely have to know this stuff to pick the right materials for building, well, everything. It's even how you check if a bar of gold is the real deal. And remember that water displacement method? It's all based on Archimedes' principle, a discovery made more than 2,000 years ago. It just goes to show how these fundamental ideas we're using today have a really long and important history in science. And that leaves us with a final thought. Literally everything around you has a mass and a volume, which means everything has a density. So what else in your world could you start to identify if you just knew how to measure it? Think about that. Thanks for joining me for this explainer.